Welcome back to the deep dive. Today, we're going to be taking a deep dive into test time computing
Okay.
and specifically how it's changing the game for AI.
Interesting.
We're going to be looking at this concept through the lens of System-1 and System-2
Right.
thinking from psychology.
Yeah.
Those like fast gut reactions versus those slower, more analytical thought processes.
Got it.
We've got some fascinating excerpts from a research paper for this deep dive
Okay.
titled Test Time Computing. From System 1 thinking to System 2 thinking.
Sounds fascinating.
It really is. I think you're going to find this really interesting.
Yeah.
So to get us started, the paper explains how test time computing uses computational resources during the inference phase
Uh-huh.
when the AI is making decisions, rather than just during training. This seems like a pretty big shift from the traditional deep learning approach.
Well, it's definitely a key difference. In traditional deep learning, the emphasis has really been on scaling during training.
Yeah.
But this new approach suggests a shift in focus. That could have huge implications for AI,
Totally.
for what AI models can achieve.
Yeah, so let's break down these two systems of thinking a little bit.
Okay.
The paper describes those System 1 models
Mm-hmm.
as the earlier AI models
Mm-hmm.
that were primarily focused on just recognizing patterns.
Yeah, think of it like instantly recognizing a face.
Right.
It's very fast, very automatic.
Right, like a gut reaction almost.
Yeah.
Whereas System 2 models are the ones capable of slower, more deliberate thought processes.
Right, more like how we'd solve a math problem.
Exactly.
Yeah.
And the paper explains how test time computing was initially used to improve the capabilities of those System 1 models
Uh-huh.
by helping them adapt to new data,
Right.
which is really important when the data used to train the AI is different from real-world data, which the paper refers to as distribution shift.
It's a super common challenge for AI models.
Right.
Imagine an AI that's been trained to identify different breeds of dogs, but only using pictures from a specific data set. It might do really well in those pictures, but then struggle when it's shown pictures of dogs in different environments or
Yes.
different lighting conditions.
Yeah, that makes sense.
That's what distribution shift is.
Interesting.
Yeah.
And the paper mentions some specific techniques
Yes.
that were used to address this, like updating the AI's parameters during that test phase
Right.
and using external information to modify the input
Yeah.
or even adjust the internal workings of the model.
Yeah, all of those techniques helped those initial System 1 models become much more adaptable
Okay.
and generalize their knowledge better. They were able to handle changes
Right.
and apply what they learned to new situations much more effectively.
Interesting.
The researchers actually even call these enhanced models weak System 2 models.
Okay, so that brings us to the more advanced models,
Right.
those exhibiting signs of System 2 thinking.
Uh-huh.
And the paper specifically mentions LLMs,
Yeah.
large language models. That's examples of this.
LLMs have actually shown some System 2 thinking capabilities
Interesting.
through a method called chain of thought prompting. It's almost as though they can generate intermediate reasoning steps,
Oh, wow.
much like a human would when working through a problem.
That's really cool.
Yeah, it's pretty interesting.
But the paper also points out that even these advanced models still face difficulties with highly complex tasks.
Well, yeah.
And that's where test time computing steps in again.
Right. The paper outlines 3 key strategies
Okay.
that are used to enhance those reasoning abilities of the LLMs,
Okay.
pushing them towards stronger System 2 capabilities.
Got it.
Those 3 strategies are repeated sampling, self-correction, and tree search.
So repeated sampling, that sounds intriguing.
Yeah.
The paper explains how it involves the AI generating multiple solutions to a problem
Right.
and then choosing the best one.
Uh-huh. It's like exploring different approaches to find that optimal solution.
So it's almost like brainstorming.
Yeah, exactly.
That's neat.
Yeah.
And then there's self-correction.
Right.
The paper describes it as a process where the AI can examine its own reasoning,
Yeah.
identify any errors, and then fix them.
It's like having the AI double-check its work,
I see.
which significantly boosts the reliability and accuracy of these models,
Makes sense.
just like it does for us.
And finally, there's tree search.
Yes.
The paper describes it as a systematic way for the AI to explore different reasoning paths to find the optimal solution.
Think of it like mapping out all the possible moves in a complex game of chess.
Okay.
The AI uses algorithms to explore all these different pathways and systematically narrow down the options to find that best solution.
Got it.
Yeah.
And the paper highlights a specific model called the O1 model.
Right.
that showcases the potential of these test-time computing techniques for unlocking advanced reasoning abilities in AI models.
This model has shown some really impressive reasoning capabilities,
Interesting.
highlighting how these strategies can lead to significant breakthroughs in AI's ability to solve complex problems.
Okay, so let's dig into the specifics of each of these three strategies,
Sure.
starting with repeated sampling.
Sounds good.
How does that actually work?
So repeated sampling is especially helpful for tasks that have verifiable outcomes,
Okay.
like, say, generating code.
Okay.
In those cases, you can really easily test if that generated solution is correct or not.
Right.
But for tasks that are more subjective,
Hmm.
like solving a math word problem,
I see.
you need a more reliable way to evaluate all those different solutions generated.
Yeah, that makes sense.
So the paper describes two common approaches:
Okay.
majority voting
Uh-huh.
and best of n sampling.
Okay, so with majority voting, the AI selects the most frequent answer from all those generated solutions.
Yeah, exactly. It's a pretty simple but effective approach,
Gotcha.
especially when the AI is generating a large number of potential solutions.
Right.
The idea is that the most common answer is likely to be the correct one.
Makes sense.
And then in best of n sampling, the AI actually uses a separate model called a verifier to evaluate each of those solutions and then picks the one with the highest score.
So it's almost like a panel of judges.
Exactly.
Interesting.
Yeah?
And the paper notes that repeated sampling,
Yes.
particularly that best of n sampling, has been so effective that it can sometimes even outperform models that have been fine-tuned with reinforcement learning
You got it.
from human feedback.
It's a significant finding
That's wild.
because it suggests that repeated sampling can be a more efficient and effective way to improve the performance of AI models for certain tasks.
Wow.
Yeah.
But the paper also acknowledges that repeated sampling does have its limitation.
Of course.
It can be computationally expensive
Right.
to generate and evaluate multiple solutions, especially for those really complex tasks.
Right. So it may not be practical for all applications.
Yeah, I see how that could be a problem.
Yeah.
And so the paper suggests that researchers are currently exploring ways to make repeated sampling more efficient. One approach involved training AI models that can directly approximate that best of n distribution,
Right.
reducing the need for extensive sampling during that inference phase,
Exactly.
which would make it much more feasible
Yeah.
for more applications.
Yeah. You got it.
Okay, so next up we have self-correction.
Okay.
How does that work?
So self-correction enables AI models to actually refine their outputs based on feedback.
Okay.
And this feedback can come from several different sources,
Right.
like external tools, other AI models, and even the AI model itself.
Got it.
And each source has its own advantages and disadvantages.
So human evaluation, for instance, is considered the gold standard,
Yeah.
but obviously it can be costly and difficult to scale.
Precisely.
And external tools like compilers for code generation,
Yes.
they can provide really precise feedback for specific domains, but their applicability is limited.
Right. Right.
And external AI models, especially those trained to be critics, offer a more generalizable approach,
Yeah.
but they can exhibit biases. And then there's the really interesting concept of intrinsic feedback, where the AI model evaluates its own outputs.
Right. Without relying on any external sources.
But the paper also mentions that the effectiveness of self-correction
Mm-hmm.
is still being debated
It is, yeah.
within the research community.
Right.
Some studies have shown it to be really effective,
Right.
while others suggest its benefits have been overstated.
Yeah, so it's definitely an area that requires further research
That makes sense.
to fully understand its potential and limitations.
Okay, so to address some of those limitations of self-correction, especially for smaller AI models, researchers are developing techniques to specifically train these models to become better at self-correcting.
Right.
So one approach is supervised fine-tuning,
Right.
where the models are trained on data sets of multi-turn corrections, either annotated manually or generated by those more powerful AI models,
Right.
which gives them more examples of how to effectively correct their own mistakes.
Exactly.
And another approach is online imitation learning,
Right.
where the AI models are continually trained on new self-correction patterns generated during the inference phase.
Which allows them to adapt to a wider range of correction strategies.
Interesting.
Yeah.
And both of these approaches aim to make self-correction a more reliable and robust strategy for enhancing AI performance.
Precisely.
Got it.
Yeah.
Okay, so finally, let's discuss the third strategy. Tree search.
Okay.
How does that one work?
So tree search basically simulates human problem solving by combining elements of parallel exploration.
Okay.
kind of like brainstorming, and sequential backtracking,
I see.
where the AI revisits alternative paths when it hits a dead end.
Interesting.
This allows the AI to explore a wide range of potential solutions while systematically narrowing down those options to find the best one.
So it's kind of like having a map of all the possible routes.
Exactly.
And you're trying to find the most efficient one.
Exactly.
Okay.
Yeah.
And the paper explains that there are two key components that drive tree search: the search algorithm and the value function.
Right. So the search algorithm determines how the AI explores that space of possible solutions.
Okay.
And there are actually various algorithms available, including uninformed search, like breadth-first search or depth-first search, and heuristic search, with Monte Carlo tree search being a prominent example.
Okay.
And each algorithm has its own strengths and weaknesses, making it suitable for different types of problems.
Makes sense.
Right.
So the choice of algorithm really depends on the specific task and the characteristics of the search space.
Exactly.
Got it.
And then the value function estimates the value of each potential action or step in the reasoning process,
Okay.
guiding the search towards more promising paths.
Interesting.
So it helps the AI prioritize which paths to explore first, focusing on those most likely to lead to that best solution.
Got it.
Yeah, and researchers are using both handcrafted and learned value functions.
Okay.
Handcrafted value functions are designed based on expert knowledge and domain-specific insights, while learned value functions leverage the power of LLMs to automatically generate reasoning steps and evaluate their quality.
So those learned value functions can actually adapt and improve over time
Right.
as they encounter more data.
Exactly.
That's cool.
Yeah, it is.
And the paper highlights an interesting variation of tree search called R-star,
Yes.
which addresses some limitations of those traditional value functions.
So instead of relying on a single value function, R-star maintains multiple candidate paths and utilizes a separate LLM to reason over them.
Okay.
And the path where both LLMs agree is then selected.
So it's almost like getting a second opinion
Exactly.
from another expert. Yeah.
Which helps to mitigate potential biases that might arise from using just a single value function,
Gotcha.
leading to more robust and reliable decision-making.
Interesting.
Yeah.
And just like the other test-time computing strategies, tree search also generates valuable data that can be used to train even more powerful AI models.
Right. Researchers are using techniques like RES-MCTS, which combines tree search with process-based rewards to collect high-quality reasoning trajectories.
Okay.
And that data is then used to improve both the policy and reward models used in AI training.
Interesting. So it's like a continuous cycle of improvement.
Exactly. As the AI reasons and explores solutions, it generates more data,
Right.
which in turn helps to create more advanced models capable of even more sophisticated reasoning.
That's pretty cool.
It is. It's really fascinating.
Yeah, it is.
Yeah. So the paper then goes deeper into the specifics of how these test-time computing strategies are actually implemented.
Okay.
And it starts with this concept of feedback modeling.
Okay, so what is that?
Well, it involves evaluating the quality of the AI's generated outputs.
Okay.
And the paper explains how a separate model, often called a verifier,
Okay.
is used to assess, how well the AI's responses align with the correct answer or the desired reasoning process.
Got it.
And there are two main types of these verifiers.
Okay.
Outcome-based. Okay.
And process-based.
Got it.
So outcome-based verifiers, they just check if the final answer generated by the AI is correct.
Okay, so pretty straightforward.
Yeah.
Okay.
Whereas process-based verifiers, those go a bit deeper.
Okay.
They examine each step in the AI's reasoning
Got it.
to provide more granular feedback.
I see.
So those process-based verifiers, they're particularly valuable for tasks that involve, complex reasoning.
Right.
They can pinpoint where the AI's logic might be flawed, offering more specific guidance
That makes sense.
for improvement.
Okay.
And the paper also discusses using LLMs themselves as verifiers,
Oh, interesting.
providing feedback in natural language.
Okay.
So this involves training a specialized LLM called a critic
Okay.
to evaluate and critique the outputs of other AI models.
Got it.
And these critics, they can provide really detailed assessments of the AI's responses, including their factual accuracy,
Right.
logical coherence.
And even, stylistic elements.
Interesting.
And the paper mentions that powerful closed-source LLMs, like GPT-4, have actually proven to be very effective critics.
Makes sense.
But researchers are also, cautious about potential biases in these advanced critics.
Right, because they could be influenced by things like the length of the response.
Exactly. Or its position within a set of outputs.
Yeah.
Or even its perplexity,
Yeah.
which is a measure of how surprising or unpredictable the text is.
I see.
So researchers are working on techniques to train critics that are more objective and less susceptible to these influences.
Right, so carefully selecting the training data and using algorithms that focus on those core aspects of reasoning and accuracy.
Exactly.
Okay.
So the paper then moves on from this feedback modeling to explore those specific search strategies used in test-time computing.
Okay.
We already talked about repeated sampling, but let's dive a little deeper into the specifics of how it's actually implemented.
Oh, good.
We discussed how repeated sampling is particularly useful for tasks with verifiable outcomes, where the correctness of each generated solution can be easily tested.
Right, like code generation.
Exactly. But for more subjective tasks, like math word problems,
Okay.
where the correctness of a solution might not be immediately apparent.
Right.
A more robust verification strategy is needed.
Makes sense.
And that's where those two approaches we mentioned, majority voting and best of n sampling, come into play.
Okay, so we already talked about how majority voting involves selecting the most frequent answer among the generated solutions.
It's a simple but effective approach, especially when the AI is generating a large number of potential solutions.
Right.
And then best of n sampling, a verifier is used to score each solution.
Okay.
And the one with the highest score is chosen.
Got it.
Which adds, a layer of sophistication to the decision-making process.
Right.
Ensuring that the solution is not only correct, but it also aligns with that desired reasoning process.
Makes sense.
And the paper points out that repeated sampling, especially best of n sampling, can be so effective that it sometimes surpasses the performance of models that have been fine-tuned with reinforcement learning from human feedback.
Wow, so it can actually outperform models that are trained with human feedback.
Sometimes, yeah.
That's fascinating.
It is.
Okay.
But as we discussed earlier, repeated sampling can be computationally expensive.
Yes.
Generating and evaluating all those multiple solutions, especially for complex tasks, requires a lot of computational resources.
So to mitigate this cost,
Right.
researchers are exploring ways to train AI models that can directly approximate that best of n distribution.
Which would reduce the need for extensive sampling during that inference phase.
Making it much more efficient.
Exactly. So moving on to self-correction.
Okay.
The paper looks at all the different sources of feedback that AI models can use to refine their outputs.
Right. So we talked about external tools, other AI models.
Right.
And even the model itself.
Right. The paper goes into, the pros and cons of each of those feedback sources.
Okay.
Acknowledging that while human evaluation is the gold standard, it's often impractical.
Right, because of cost and scalability.
Exactly.
And external tools, things like compilers for code generation.
Right.
They can give really accurate feedback.
Yes.
But only for specific domains.
Right.
Their applicability is limited.
Exactly.
And then external AI models, like those critics, they offer a more generalizable approach.
Right.
But we talked about how they can sometimes be biased.
They can.
And the paper also discusses this concept of multi-agent debate.
Oh, yeah.
Where multiple AI models actually engage in a dialogue.
Right, to critique each other's reasoning.
Wow.
And reach some kind of consensus.
That's so cool.
It's a really interesting approach. But it can be challenging to ensure that the models remain objective and aren't influenced by, adversarial inputs.
Right, because they could end up in an argument.
Exactly.
Or something.
Yeah, and then there's the idea of intrinsic feedback.
Right, where the model is evaluating its own outputs.
Exactly, without relying on anything external.
Okay.
And this relies on the principle that verifying a solution is often easier than generating one in the first place.
Okay.
But the effectiveness of this self-correction has been debated within the research community.
Yeah. Some studies say it's good and others say it's not as good as we think.
Exactly. And the paper acknowledges this, emphasizing the need for more research to really understand the limitations and best use cases for self-correction.
Makes sense.
So to address some of those limitations of self-correction, especially for those smaller AI models, researchers are developing techniques to train them to be more effective at self-correcting.
Got it.
So one approach is this supervised fine-tuning.
Right, where they're trained on data sets of multi-turn corrections.
Exactly. Either annotated manually or generated by more powerful AI models.
Oh, yeah.
And this provides them with really explicit examples
Right.
of effective self-correction strategies.
So they're learning by example.
Exactly.
Okay.
And another approach is online imitation learning.
Right, where they're continually trained on new self-correction patterns.
Right, during the inference phase.
So they can adapt to a broader range of correction patterns.
Exactly.
Yeah.
And both of these approaches aim to enhance the reliability and robustness of self-correction as a strategy
Okay.
for improving AI performance.
Got it.
And then finally, let's delve into the third search strategy,
Okay.
tree search.
Okay, how does that one work?
So tree search simulates human-like problem solving by combining elements of parallel exploration,
Okay.
kind of like brainstorming,
Right.
and sequential backtracking,
Yeah.
where the AI revisits alternative paths
Okay.
when it encounters a dead end.
Interesting.
And this approach allows the AI to explore a huge range of potential solutions
Right.
while systematically narrowing down the options
Okay.
to find the best one.
So it's kind of like mapping out all the possible routes on a map
Exactly.
and trying to find the most efficient one.
Yes.
Okay.
And the paper explains that there are two key components that drive this tree search: the search algorithm and the value function.
Yeah.
So the search algorithm determines how the AI explores that space of possible solutions.
Okay.
And there are various algorithms available, like uninformed search, things like breadth-first search or depth-first search, and then heuristic search, with Monte Carlo tree search being kind of a prominent example.
Okay.
And each algorithm has its own strengths and weaknesses, making it suitable for different types of problems.
So it depends on the task,
That's
thematic
right.
characteristics of this search space.
Right. And then the value function, it estimates the value of each potential action or step in the reasoning process,
Okay.
guiding the search towards more promising paths.
I see.
So it helps the AI prioritize which paths to explore first, focusing on those most likely to lead to the best solution.
Got it.
And researchers are using both handcrafted and learned value functions.
Right. So handcrafted ones are designed based on expert knowledge.
Yes, and domain-specific insights.
Okay.
While learned value functions leverage the power of LLMs
Okay.
to automatically generate those reasoning steps and evaluate their quality.
So those learned value functions can actually adapt and improve over time.
Exactly, as they encounter more data.
Okay, that's cool.
It is, yeah. And the paper mentions this interesting variation of tree search called R-star,
Yes.
which addresses some limitations of traditional value functions.
So instead of relying on a single value function, R-star maintains multiple candidate paths and uses a separate LLM to reason over them.
Okay.
And the path where both LMs agree is then selected. Interesting. So it's like getting a second opinion from another expert.
Exactly,
Well-
which helps to mitigate those potential biases
Right.
that might arise from using just a single value function,
Got it.
leading to more robust and reliable decision-making.
Interesting.
And similar to those other test-time computing strategies we talked about,
Uh-huh.
tree search also generates valuable data
Right.
that can be used to train even more powerful AI models.
Okay.
Researchers are using techniques like REST-MCTS, which combines tree search with process-based rewards
Right.
to collect high-quality reasoning trajectories.
Sorry.
And that data is then used to improve both the policy and reward models
Okay.
used in AI training.
So it's a continuous cycle of improvement.
Exactly. As the AI reasons and explores solutions, it generates more data,
Right.
which in turn helps to create more advanced models.
That are capable of even more sophisticated reasoning.
Precisely.
The paper also highlights this challenge of balancing the trade-off
Right.
between reasoning efficiency and performance.
So, test-time computing,
Uh,
it often involves a lot of computational resources,
it does.
which could limit its use in the real world.
Right. Finding ways to make test-time computing more efficient
Yeah.
without compromising performance
Right.
is going to be really crucial
Yeah.
for its wider adoption.
Makes sense.
And researchers are exploring a bunch of different approaches to address this challenge.
Like what?
Well, one promising approach is to develop models that can adaptively allocate those resources
Okay.
based on how complex the task is.
So the AI would assess the difficulty
Right.
of the problem and then adjust its reasoning effort.
Exactly. So for simpler tasks, it would use fewer resources.
Okay.
And for more complex tasks,
Yeah.
it would allocate more resources to make sure it gets accurate and reliable results.
Okay. So it would know when to put in more effort
Right.
to get a better result.
Exactly.
That's cool.
And another crucial area for future research is developing a universal scaling law for test-time computing.
Okay, what's that? Well, unlike training time scaling,
Ah,
which has, well-established principles,
right.
test time computing still doesn't have a clear understanding of how performance scales with computational resources.
I see.
So developing that kind of scaling law would give us some really valuable
I
insights
like it.
into how to optimize these strategies and how to predict how effective they'll be.
So it would help us make better decisions about which strategies to use
Exactly.
and how to allocate our resources.
Right.
Interesting.
And finally, the paper emphasizes the potential of combining different test time computing strategies
All right.
to create even more powerful and versatile AI models.
That makes sense.
Each strategy has its own strengths and weaknesses,
Right.
and by integrating them, you could lead to systems
Mm-hmm.
that leverage all the benefits.
So it's like combining the expertise of different specialists
Exactly.
to solve a complex problem.
To get a better outcome.
Right.
That makes a lot of sense. So the future of AI might very well lie in these hybrid systems that leverage the strengths of all these different test time computing strategies.
It's clear that test time computing is a really rapidly evolving field
It is.
with so much potential
Definitely.
to reshape AI.
Absolutely.
As researchers continue to explore and refine these techniques,
Yeah.
we can expect to see even more groundbreaking advances in AI's ability to reason, problem solve, and learn.
It's a fascinating area of research for sure.
It is.
And its impact is going to be huge.
Well, thanks for joining us on this deep dive into the world of test time computing.
Yeah, thanks for having me.
We hope you found it insightful.